Hello, my name is Andrew Gary, and welcome to Seismic Sound Off, in-depth conversations in applied geophysics. In this episode, I speak with Yilmaz on his latest book, Land Seismic Case Studies for Near-Surface Modeling and Subsurface Imaging. Written for practicing geophysicists, this book is a culmination of land seismic data acquisition and processing projects conducted by Oz over the last 2 decades. Containing nearly 800 figures from worldwide 2D and 3D case studies, it is a comprehensive guide to understanding the acquisition, processing, and analyzing of seismic data. In this episode, Oz shares why marine versus land seismic makes an important difference, why the image-based workflow described in the book matters to geophysicists, the criteria for a migration algorithm to qualify as a depth migration algorithm, one of the most likely applications of artificial intelligence for seismic data analysis, and more. Oz's expertise and experience are highlighted in detail in this revealing and essential conversation. This episode is brought to you by CGG. Sometimes the toughest challenges are the ones right below your feet. The near surface is notorious for generating a host of issues for seismic imaging, and overcoming these challenges demands experience and the latest technology. For over 90 years, CGG has championed the latest seismic advancements. From industry-leading surface wave inversion and advanced D-multiple algorithms to the high-performance computing required for modern land datasets, CGG can help you tame the near surface so you can image the deep. Let CGG help you to see things differently. Visit seg.org/podcast for the link to Oz's book and a bonus clip highlighting the case studies presented in the book. Now, for our conversation. So Oz, you recently published Land Seismic Case Studies for Near-Surface Modeling and Subsurface Imaging. The prior book was on engineering seismology. How did your work on engineering seismology projects inform your work on exploration seismology?
Andrew, in 2001, I decided to focus on land seismic exploration. There were many challenges regarding the near surface to confront. The complexity and heterogeneity of the near surface that give rise to travel time and amplitude distortions associated with subsurface reflections, and surface waves that consume most of the seismic source energy, leaving very little to penetrate into the subsurface. So to understand the wave phenomenon in the near surface in close proximity, I conducted numerous engineering seismology projects that required detailed seismic characterization of the near surface. What I then learned from the engineering seismology projects with regards to the nature of seismic wave propagation in the near surface, I transfused into exploration seismology.
Why does the medium for marine and land seismic make such a big difference?
Marine seismic source and receivers are deployed on a flat datum in a water layer that represents on a macro scale essentially a homogeneous medium. In comparison, land seismic source and receivers are deployed on an irregular topography over a near surface that often represents a heterogeneous medium. This difference between marine and land seismic exploration has an enormous impact on the quality of the data acquired. What is the one challenging problem in marine seismic? Attenuation of various types of multiples, water bottom, surface-related, peg leg, intra and inner band multiples, and diffractive multiples. Additionally, a shallow water layer gives rise to not only short-period multiples and reverberations, but also beyond the critical angle of propagation, dispersive guided waves trapped within the water layer, traveling in the horizontal direction with linear movement. So multiple attenuation is indeed a key problem in marine seismic exploration. And what is the one challenging problem in land seismic? In land seismic exploration, data often are acquired over an irregular topographic surface and complex near surface. The near surface is defined as the depth interval below the free surface up to a few hundred meters of thickness, composed of a low-velocity soil column and unconsolidated, heterogeneous, and weathered layers of rock. There are two deleterious effects of the near surface. A, the near surface causes distortions of subsurface reflection travel times and amplitudes. And B, the near surface gives rise to dispersive surface waves and guided waves, which can severely mask subsurface reflections in recorded data. Now, to solve the first problem, we need to estimate a velocity depth model for the near surface, then calculate and apply shot receiver statics corrections. Nevertheless, none of the methods for near surface modeling, including FWI, can resolve very short wavelength velocity variations in the near surface, which give rise to short wavelength reflection travel time distortions. This means that we also need to estimate and apply residual statics corrections. This is an indispensable and irreplaceable step in lens seismic data analysis. To solve the second problem, both guided waves and surface waves are treated as coherent linear noise generated by and trapped within the low velocity near surface region traveling in the horizontal direction. They do not contribute to the subsurface image. The linear move-out character of surface waves, however, often is disrupted by backscattering and backpropagation as a result of irregular topography and the near-surface heterogeneity. Surface waves need to be removed by an appropriate sequence of single and multi-channel filtering to unravel weak reflections. So, resolving the deleterious effects of a complex near surface with irregular topography is indeed a key problem in land seismic exploration, Andrew.
Well, that is a tremendous summary there. Packed a lot in that response. What negative effects does the near surface contribute to seismic acquisition?
The land seismic source and receivers deployed in the heterogeneous medium of the near surface give rise to complex radiation patterns of the seismic source energy with significant wave mode conversion, Andrew. Unlike the marine seismic source wavelet, the land seismic source wavelet, immediately after the onset of the source excitation, is subjected to severe amplitude and phase distortions and intrinsic attenuation of high frequencies. Most of the seismic source energy is consumed by surface waves and guided waves trapped in the near surface. The complexity of the near surface often gives rise to backscattered and backpropagated surface waves, as we said earlier, with complex move-out that departs from the linear move-out. Only a tiny fraction of the source energy survives the near surface, transmits into the subsurface, and gives rise to reflected and diffracted waves. On the return path, the reflected and diffracted waves from the subsurface encounter the near surface once more before being captured by receivers at the surface. A complex near surface with irregular topography often makes it compelling to record data with irregular geometry. A crooked line geometry or irregularly deployed shots and receivers in 3D surveys give rise to variations in the quality of velocity analysis and adversely affect the performance of multi-channel signal processing algorithms. Additionally, variation in fold of coverage resulting from irregular geometry causes amplitude variations in subsurface imaging.
Why will the image-based workflow for near-surface modeling you describe in the book appeal to practicing geophysicists?
The iStats image-based workflow for modeling near-surface anomalies does not require first break picking as for travel time tomography, does not require source wavelet estimation as for full wave inversion, does not fail velocity reversal in the near surface, as in travel time tomography, does not suffer from velocity depth ambiguity, does not require data modeling, travel time or wave field modeling, as for any inversion method, and does not exhaust computational resources, as in full wave and joint inversion.
How does residual statics play a role in producing a high quality image?
In addition to the medium to long wavelength statics, shot receiver statics also may exhibit short wavelength variations, which arise from the rapid changes in topography along the line traverse or over the 3D survey area. However, any remaining short wavelength statics that have not been resolved by near-surface modeling also are considered as residual time shifts and estimated in a subsequent stage in data analysis by surface-consistent residual statics methods. Now, I have to re-emphasize this. Residual statics estimation, therefore, is an indispensable and irreplaceable step in lens seismic data processing. You need to estimate and correct for residual statics prior to applying any multi-channel filtering to pre-stack data. And you need to estimate and correct for the residual statics to obtain a high-fidelity CMP stack and high-fidelity images from pre-stack time and depth migrations. As demonstrated by several case studies in the book, oftentimes you need to cascade refraction residual statics corrections and reflection residual statics corrections to remove the short wavelength reflection travel time distortions.
Is there an important distinction between a complex structure and a complex overburden structure?
That is a very important question. It is important to distinguish between a complex structure and a complex overburden structure. If your target is a complex structure, you can be content with an image in time generated by pre-stack time migration. If your target is a complex overburden structure, strictly speaking, you need an image in depth generated by pre-stack depth migration. For example, if your target is a complex imbricate structure associated with overthrust tectonics with an overburden of clastics with mild to moderate lateral velocity variations within the bounds of pre-stack time migration, then RMS velocity estimation based on hyperbolic move-out assumption and pre-stack time migration usually are adequate. If, however, your target is deeper and beneath a complex imbricate structure that gives rise to strong lateral velocity variations, which in turn give rise to complex non-hyperbolic move-out, then interval velocity estimation and pre-stack depth migration become imperative, Andrew.
What are the criteria for a migration algorithm to qualify as a depth migration algorithm?
There are three criteria for a migration algorithm to qualify as a depth migration algorithm. First and foremost, the algorithm of our choice must be able to image steeply dipping reflectors in the presence of strong to severe lateral velocity variations. Second, 2D and 3D pre-stack seismic data invariably suffer from irregular spatial sampling. Therefore, the algorithm of choice for pre-stack migration must cope with irregularly sampled data. And third, just as we use pre-stack time migration to estimate and update RMS velocities, we often wish to use pre-stack depth migration to estimate and update interval velocities. Now, the Kirchhoff migration meets the requirements for irregular spatial sampling of recorded data and velocity estimation and updating. Reverse time migration, on the other hand, meets the requirement for steep dips in the presence of strong to severe lateral velocity variations even for dips greater than 90 degrees, such as in the case of salt overhang structures. So to meet all three requirements for precise depth migration, however, we can make combined use of Kirchhoff migration and reverse time migration. Specifically, we can use Kirchhoff migration for image-based velocity depth model estimation and iteratively updating the estimated model by residual move-out analysis of SIP gathers associated with precise depth migration to correct for velocity errors based on the flatness of events in the SIP gathers. Then, using the final velocity depth model, we can perform reverse time migration to obtain the subsurface image with the required accuracy. Keep in mind, though, that RTM, reverse time migration, being a highly accurate migration algorithm, is significantly more sensitive to velocity errors than Kirchhoff migration, which better responds to a smooth interval velocity field.
Yeah, it's a helpful reminder there. And I want to look at another workflow that could be appealing to practical geophysicists. Why is the image-based workflow for subsurface velocity estimation that you also describe in the book, why would that also appeal to practicing geophysicists?
Now, the objective is to circumvent the velocity uncertainty in cases of complex structures that we have talked about. Velocity uncertainty invariably gives rise to erroneously high or low migration velocities, which then causes two problems with pre-stack migration. A, we fail to preserve reflector amplitudes, and B, we also fail to position the reflectors correctly, and we fail to focus diffractions to their apexes. We may choose to solve both problems simultaneously or one after the other. The quality of image gathers associated with pre-stack migration, however, may or may not warrant the simultaneous solution. In areas with irregular topography, complex near surface, and complex subsurface, it may not. So I propose in Chapter 7 of the book the iCube image-based workflow to circumvent the velocity uncertainty, applicable to both 2D and 3D seismic data, to solve the two problems with pre-stack time migration, one after the other. The iCube workflow includes synthesis of a zero-offset wave field, followed by zero-offset time migration, and time-to-depth conversion of the time-migrated zero-offset wave field, or zero-offset post-stack depth migration. The iCube workflow involves demigration of the image panels of the migration volume used for velocity estimation to preserve event non-stationarity. This is necessary for weighted summation of the image panels of the demigration volume over the velocity axis so as to obtain a synthesized zero offset wave field to capture and preserve all reflections and diffractions.
What does a geophysicist need to be cognizant of when applying full waveform inversion to land seismic data?
Anyone interested in applying full wave inversion to land seismic data for near-surface modeling should be mindful of the results of the field experiment described in the introduction chapter of the book. 1. Seismic wave amplitudes are significantly more prone to noise than travel times. In the case of travel time tomography, you have the opportunity to edit the first arrival travel times picked from shot gathers, discard some, and correct some, so that the travel time set input to inversion is entirely within your control. In contrast, though, you do not have the same opportunity with the wave amplitudes, except for some simple signal processing, such as narrow bandpass filtering. The second point, in order to meet the requirement that the input shot gathers approximately represent acoustic wave fields, you may want to use the early portion of the recorded data that may be treated as a representation of the seismic waves confined to the near surface region. However, the radiated energy associated with a vertical impact source applied to a very low velocity near surface, for which status corrections are significant, is composed of Rayleigh-type surface waves and a mixture of PP, SS, PS, and SP converted wave modes. Now, this alone disqualifies acoustic wave inversion applied to land seismic data for near-surface modeling. The third point is that you may want to be less ambitious and apply acoustic wave inversion to early arrival waveforms, which can be assumed to be associated with P waves only. Unlike the subsurface, the near surface can be highly heterogeneous, strongly anisotropic, highly attenuating, and even poroelastic in nature. Therefore, full wave elastic inversion would even be a futile exercise if these characteristics of the near surface are not accounted for. The fourth point is, rather than starting the FWI iteration with an initial model that is very different from the true model, we can gain computational savings if we start the iteration using the output model from travel time inversion, a model that is closer to the true model. Cascading travel time inversion with full wave inversion in this manner also can reduce the required number of iterations and increase the convergence rate in full wave inversion. Finally, for full wave elastic inversion, you may try performing travel time tomography to estimate a P wave velocity depth model for the near surface and Rayleigh wave inversion to estimate an S wave velocity depth model for the near surface. Then use the resulting pairs of models as the initial models for the subsequent full wave elastic inversion, Andrew.
That is a nice, thorough response there that I'm sure goes more in depth in the book. What kind of switching gears a little bit here, what do you see as one of the most likely applications of artificial intelligence for seismic data analysis?
In recent years, machine learning algorithms have been experimented with for first break picking, surface wave suppression, velocity picking, and even for velocity depth model construction, Andrew. Most of such experiments have relied on synthetic data, and the tests with field data have not yielded convincingly superior results compared to conventional methods. Perhaps the most successful application of machine learning has been in seismic interpretation and combined utilization of diverse exploration and production data. Now, I myself, with a collaborative effort, have been experimenting with machine learning algorithms to pick extremely difficult cases of first breaks, extremely ambiguous cases of velocities, and suppress highly complex surface waves. So far in the industry, we have yet to see convincingly successful results of machine learning in all these applications. Now, whether it's artificial or natural intelligence, the strategy for deriving a structurally consistent RMS velocity field must be volume-based picking rather than picking semblance spectra in isolation. And a sound strategy is to use a set of velocity functions conventionally picked from semblance spectra as a training data set for machine learning.
I want to just lastly here, why did you dedicate this book to Luger Mintrop, Reginald Fessenid, and Clarence Karcher?
In 1921, Clarence Karcher and his co-workers, based on technology developed by Reginald Fessenid, designed and conducted the first reflection seismic experiment in Vine Creek, Oklahoma, for petroleum exploration. So by this field experiment, Andrew, reflection seismology was proven as a valid method in the search for oil. Thus was the birth of the reflection seismic method. So the publication of this volume fortuitously coincides with the centennial of this major event that set the beginning of the seismic industry. And we shall celebrate this centennial of the reflection seismic method during the SCG meeting in September.
So, Oz, thank you for this conversation and for sharing about this book. I'm sure many are eager to get their hands on this book, and thanks for outlaying so much of the valuable content that people can expect in your latest work.
Thank you, Andrew. Thank you very much.
Thank you for listening to SEG's flagship podcast, Seismic Sound Off. SEG produces these episodes to benefit its members, the geophysics community, and inform the public on the value of the science. To show your support for the show, please share this episode with a friend, colleague, or manager that would enjoy hearing this show. Your recommendation is the single best action you can take on behalf of SEG's podcast. To receive the latest episodes first, follow Seismic Sound Off on Apple Podcasts, Spotify, or Google Podcasts. The SEG podcast team is Ted Bakamjian, Kathy Gamble, and Ali McGinnis. Thank you for listening. This is Seismic Sound Off, signaling off.